Good morning, class. How's everybody doing today? I hope you're doing well. I was going for like a Homer Simpson thing, with the contrast of the colors right on the screen right now. However, I'm not quite satisfied. It's not yellow enough for me, so I'm gonna try turning up the saturation. See if that. Yeah, there we go. And can we get it like perfectly? I don't think I think I'm gonna end up a bit orange, but that's okay. There. Okay. Cool. So, yeah, I don't know. Might as well get right into it. Um, let's talk about functions and recursions as we have been up to this point. We're kind of behind, so we might as well just get right into it. So, last time we had started talking about searching algorithms. We'd started with unstructured search, which is just, you check every element in the array to see if any particular element in the array is the... Whoops, I'm using C language again. That's what we call lists in C, is arrays. Technically speaking, arrays are a much more basic data structure than lists. They have a lot less going on. Hello? Hello? Have you been thrust into the spotlight? Whoop, whoop. Come, ouch, oh, there. Come on, there we go. You have to give everybody their morning cuteness. Oh, there we go. Alright. So, whoop. There we go. With linear search, because you can't make any assumptions about the data, you can't assume any particular... There are no properties to help you out. So, yes, I know. Here. Go! Believe it or not, she plays fetch with a little purple pom-pom, which is her favorite thing in the universe. I can't right now. I'm streaming. I know. Here. Meow. There we go. Anyway. Gonna try to ignore the cat and continue the lecture. Generally speaking, the way that algorithms design works, you have data, and you can assert mathematical properties of that data. And when I say mathematical properties, I'm sort of talking about things in the category of, can we assume orderedness? Can we assume that this element is always going to be greater or less than that element? Can we assume, things like commutativity and idempotency and all of these crazy mathematical terms that you'll probably hear quite a lot of if you are in comp sci and you go on to study algorithms properly. Otherwise, I don't know, probably the mathematicians in the crowd know what idempotency is, but it's not you don't have to worry about it. It's not going to be on the test or anything. I'm just using fancy words. But so, generally speaking, it is by taking advantage of the mathematical properties, the provable mathematical properties, or the assumable mathematical properties of a set of data, that we can come up with better algorithms to work with the data. A very good example of this is the idea of sortedness. So data is sorted if that data is in order according to some means of comparison. With respect to integers, it's reasonably straightforward. We consider ordering over the integers to be the thing that equality, or inequality, inequality comparisons check for. So if a number is less than another number, it would come before that number in an ordered data set. So with respect to, the properties of ordered data sets, it is often the case that you can improve certain operations over ordered data sets. You can improve the amount of time they take to execute so radically that it is worth the extra overhead to either sort them in the first place or keep an ordered data set sorted. So you can sort of imagine if you wanted to add an element to a sorted array, it is not too bad an operation to find the correct place for it in the array and sort it and insert that element into the... You know what? I've been doing so many arrays in C lately that I'm probably going to say the word array a lot. I hope you'll forgive me. When I say array, just insert in your brain the word list or tuple, or, you know, structured data set. One of those things. So when you... What was I saying? Something about inserting. Yeah, so when you take an element and you insert it into an already ordered list, the amount of, like, the number of operations, the number of comparisons that you have to perform in order to find the correct spot is at most the size of that array, which makes it a big O of n algorithm. Whereas, in order to sort an array that is completely unsorted, that takes longer because you have to sort everything in the array. So keeping data sorted is easier than sorting it. And performing search operations over sorted data is much, 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 much faster than performing a search operation over unsorted data, as we shall see. And that's kind of interesting because this is already a big O of n algorithm. So there you go. Let me see what chat has to say. Cats are liquid, yes. The viewers are going down. Concurrent viewers 81. That's okay. I'll make it public after we're done. And you know, the whole point of this is that you can kind of watch them synchronously or asynchronously, however that fits your schedule better. Who knows? Maybe people have a lot of midterms they have to study for. So question, when you put a range as range 0 to the length of L, wouldn't there be an indexing error because the indexing ends at L minus 1 because indexing starts at 0? Well, that would be the case, except that when you ask for a range, it actually excludes that last parameter. So if you go from 0 to 10, you'll notice that the 10th, this is the 10th element. So the actual value of 10 is excluded, so that actually isn't such a problem. There you go. When would you use length of L minus 1? That would be when you're... well, first of all, you would do length of L minus 1 rather than putting the minus 1 inside of that, because that doesn't make sense, because that's a... subtraction doesn't make a whole lot of sense when applied to a list. You would use that in a case where you were doing manual indexing using while loops rather than using a for loop. But even then, like, your while condition would be something like I less than or equal to length of L minus 1. Typical standard practice is just to make it an inequality, a strict inequality, rather than making it, less than or equals to, and then you can remove the minus 1. So, yeah, there you go. Good. So, if the list is sorted, then we can make use of this organization to make the job easier. The idea is, we assume the list is ordered in increasing order. We look, okay, so it's describing an algorithm here that we haven't actually seen, like we haven't named yet. This algorithm that I'm about to describe is known as binary search. Binary search is an extremely powerful algorithm. As we shall see, its performance characteristics are really, really good. In terms of the mental framework that you should be in to try to understand binary search, I would ask you to cast your mind back into the misty annals of the past, and back to the first example that we did in this entire course, which was the Newton's method of trying to find the x-intersect of a function by closing the gap. Yes! Meow! Go! That algorithm, the mechanism of that algorithm, where you have an upper bound and a lower bound, and you increasingly narrow that upper and lower bound until you hit the particular, close to the particular value you're looking for, that is a very similar thing. It's very similar to binary search as it's applied to, if you were to take binary search and apply it to a continuous function, you'd basically end up with that. So, this is how you would do a similar sort of operation over a list. So, first, we look at the entry in the middle of the list. If that entry is equal to the target entry, or the thing we're looking for, then we have found the thing we're looking for, and we can stop. If the middle entry is larger than the target entry, then we only need to look in the first half of the list. So you would then move that upper bound down, and then you would only have to worry about the lower half of the list. So the idea is, because the data is sorted, if the element in the center of the list is larger than the thing you're looking for, then because because everything higher than the middle entry is going to have a higher value, and the middle entry has a higher value than the thing you're looking for, that the thing you're looking for is going to be in the other half of the array. So that's how that works. You meow too much. Come here. I know. There. I'm going to hold you. So, and similarly, if the middle element is less than the element you're looking for, then the converse is also true. The item that you're looking for is absolutely going to have to be in the top half of the array. So, you can see how we're sort of narrowing in these two bounds. So if you think about the problem as taking bounds and moving them in, that's sort of implicitly framing this algorithm to use looping to accomplish its task, and while loops as well, not for loops. However, if you conceptualize this algorithm as a narrowing of a search space, and if you consider the portion of the list that is represented by the new bounds to be a sublist, if you consider that to be a list but smaller, implicitly that mental framework is setting you up for a recursive solution to the problem. And the way that we're going to go about solving this problem is the recursive solution. However, I'll probably show you the other one too, just so you guys are probably going to be interested in it. Questions? Is this similar to convex search? I'm not actually I'm not familiar with convex search. Sorry. What is the runtime of binary search if you include the time it takes to sort the list? Well, it would be the time it takes to sort the list. Yeah. Merge sort plus binary search. Yeah, maybe. There are pretty good sorting algorithms, but no sorting algorithm beats binary search, because the thing you're trying to do is less complicated, right? Do search engines like Google use binary search to look up entries, or do they have a more powerful algorithm? Well, I'm gonna take that question and put it to the side and allow you to make the decision yourself as to what Google has to be doing in order to achieve the types of search times that it achieves. Um, yeah. So yeah, that's a May. That's the correct way to think about it in the recursive sense. Is that we are narrowing the search space by half each step. So we're let's do let's see, implementation. No, okay. So this is how it works visually. So let's imagine we have an array. It is in sorted order. We are looking for 33. We examine the middle element. That's 22. 22 is less than 33, so we know that 33 has to be in this higher portion of the array from 23 to 63. The middle value there is 43. 43 is not 33, but it's greater than 33. So we know that the element that we're looking for has to be in the lower half of that subarray. I'm saying array an awful lot. Sorry about that. We then look at the middle element again. We get 29. That is less than, so we go higher. 32 is not 33, but it is the only element left in the array. Therefore, we have failed to find the value of 33 in the array. Therefore, we return a negative result on that. So there you go. Cool. So let's try to come up with an implementation of this, just for fun, just because it's a good exercise. I know that I'm sort of dwelling on this information a lot. It's like he keeps saying that he's, behind, but he also just does all of these, examples and things. And that's because I consider it very, very important that this material be taught well and not quickly. Because this is stuff of genuine importance. So, let's get it. Bin search. .py. So, def bin search. It will take a list, and it will take an element. So, this is going to be a recursive algorithm. The first thing that we do is we say, okay, what is the middle value? So, mid is equal to L at some index. What index, you may say? Well, how do you get the middle index? You take the length of this array and you divide it by 2. Now, the problem with division by 2 is that you may end up with 0.5 in your result. So rather than use floating point division, let's use integer division so that there's no decimal remainder. We then perform actions based on the value of the midpoint. If the midpoint is equal to let's make this algorithm return the index at which the value is found. Else, if mid is greater than E, remember, if the midpoint is greater than the element we're looking for, then it must be in the lower half of the array. Return bin search. So there we have the recursive call of some modification of L, and we're still looking for the same element. So I'm going to do this using list slicing because it's convenient to do so. We start at the beginning of the array, so that's just, we leave that one blank, and we want to go to one one index before the element that we just tested. So that would be, you know what? Wow, that's okay. I'm rewriting this expression a lot, but whatever. Remember, in list slicing, the slice is exclusive of the number that you put as the second argument. So that sort of does by default what we want it to do. Good. In the rest of the cases, the midpoint is less than e. So we will return another recursive call to bin search over a slice of the list. This time, however, we want to go all the way to the end of the list, so we leave the second argument blank, and the first argument becomes 1 plus the middle element that we were testing. And remember, the slice is inclusive of this first argument, so we have to add 1 manually. So there we go. Oh, nope, sorry. There is one case that we haven't accounted for yet. Less than e. So, if the midpoint is equal to e, then we return that. Else, if the midpoint is not equal to e, and the length of L is equal to 1, we return false. That'll be our failure condition. So, it's important to remember to put both base cases in. Because this is a search operation, it could either succeed or fail, so obviously both of those possibilities need to be represented in the code. So, questions? Burp, burp, burp. What if it is an even set of, what is it? Okay, so what if there's an even number of elements? It doesn't really matter. As long as you pick, as long as you pick a value that's, you know, close to the middle, it'll still work pretty much the same way. If the middle value isn't exactly the middle value, but is like, you know, displaced by half to one side or the other, it doesn't actually affect the runtime of the algorithm appreciably. So if it's even, you just, as long as you're rounding to a whole integer for the index, then you're fine. Yeah, Nathan has the idea. What does the parameter e represent? That is the element that we are searching for. Why do I have L in front of your equation in the mid? Why do I have L in front of my equation? Good, what? Oh, because I'm getting the value of L at that index. That's how you do that. So, just for the sake of interest, I'm going to have this algorithm generate a random array. Size 50. Well, let's make it there, so that we have a reasonable chance of hitting the thing that we're actually looking for. So let's print the result of bin search of L looking for 77. Why not? And let's put some print statements into bin search itself. Print, see what I mean with the printfs? Executing bin search over L is equal to, and then we insert L print mid is equal to mid. That should be interesting. Python 3 bin search dot py. Oop. Int object is not iterable. Did I put a 1 instead of an... Did I do a dumb thing? I think I did a dumb thing. Int object is not iterable. What? I might be getting the name wrong. Python rand int. Am I getting it right? Yeah, in case you guys were wondering how to get random numbers, by the way. Rand int AB returns random integer. Yep. Random.randint. Oh! Silly me. In order to concatenate it to an array, it has to be an array itself. It's the little things. It's the little things. Okay, so here we go. I'm going to pull that size of that down just a little bit so that we can see what's going on screen. Okay. So, obviously, you know, I'm just generating a sorted list so that we can do something. Oh, but it won't ever find 77 inside of that range, will it? Let's make it 27. Okay. So, here we go. This is the array that we are looking through. So we are performing, remember, we're looking for 27. Upon visual inspection, you can see that 27 isn't actually in the list that we're searching, but we are executing bin search over the full list. The midpoint is 21, so it goes higher. That is, the midpoint, new midpoint is 47, so it goes lower. Midpoint is 39, so it goes lower. Then the midpoint is 23, so it goes higher. It's 31, but there's only one element left, so it says false. It fails to find it again. Fails to find it again. Fails. Whoop. Traceback. Index out of range. Interesting. So this is why you test your code. So apparently, in this particular instance, we failed to account for the case where you're trying to search an empty list. Obviously, if you're searching an empty list, you're not finding the thing you're looking for, and you can actually replace this with that. Haskell guys will be familiar with that type of construction, and it should catch that case. Okay. We need to test for that before we actually calculate the midpoint. This is good. This is, you know, I always think it's good some people would be like, oh, you shouldn't make mistakes in your programming in front of a class, but I think it's more useful for you guys to see how you fix a mistake, rather than, be too worried that they happen. Aha! So, in this particular case, we actually do have 27 existing inside of the array. Now, the interesting thing about this solution is that this is not the index that we were actually hoping. Like, if you want the index of the element you're searching for, generally you want it within the context of the original array, not this sub-array. That's, like, wrong and bad. So, some additional bookkeeping would be necessary in order to make sure that that index is the correct value, but I'm not going to do that because we need to keep moving. Yep. Okay, yeah. So that's binary search. This is the version that's in the slides, which I think is reasonably similar. Yeah, it's just assigning like the mid-index and then using that through, which is fine. Makes a little more sense, actually. So, binary search using recursion is much faster because it only has to look at a small number of items in the list. So you can see, if you were to compare this algorithm to the sort of brute force linear search algorithm, linear search has to examine a lot more elements. Binary search only has to examine a very small number of elements comparatively. In fact, because of the way math works, the number of elements that binary search has to examine in order to find or not find the element you're looking for is actually log base 2 of the number of elements in the list. So what that means, I forget how to do log base 2. Is it log 16.2? Something like that? Import math. Math.log 16.2. Is that correct? Yes! So, when you're using log, if you provide one argument, it assumes you mean base 10, but if you provide a second argument, it'll use whatever that is as the base of the logarithm. So, log base 2, 16. To search 16 elements, it takes 4 steps. To search 1,000 elements, it would take at most 10 steps. To search 1 million elements, it would take, that's 10 million elements, 24 steps maximum. To search that number of elements, it would take 54 steps at maximum. So you can see that this is a very good algorithm. It is improbable that there are a number of elements, like entries in whatever tables that Google uses, that are the size of this. Right? Like, even if you're working in petabytes, how big is a petabyte again? I think it goes mega, giga, tera, peta. How big is a petabyte? It's e to the 15. So, let's see. Can you just use that notation? Maybe you can. E to the 15. Yeah. So, you can search a petabyte of information in 50 operations. Conceptualize that. Of course, it all has to be ordered. But that's, Like, the scale at which this is an efficient algorithm for large data sets is incredible. Now, I ask you, given that Google is able to search the entirety of the, well, most of the Google registered internet, shall we say, in 0.61 seconds for this result, I ask you, do you think they're using this type of an algorithm to accelerate their search process or not? Because do you think you'd be able to do linear search in that amount of time? I highly doubt it. So, yes, the version on the previous slide is still somewhat inefficient since it creates a new list every time by slicing. The next slide shows binary search using recursion by keeping track of the start and end points of the sublist rather than making a new list each time. Yes, so if you keep track of a high and a low and just update those rather than performing a list slicing operation, if you remember, list slicing is a immutable operation, so it actually produces a copy of this, like the slice is a new segment of memory each time. Although the because of the way math works, the amount of extra memory that will be designated will never be greater than the amount of memory that is occupied by the list itself, right? Because you allocate half that list, then you half of that, half of that, half of that, half of that. It'll all fit inside of that. Still, if you're working with very, very large data sites, like a petabyte of information, you don't want to have to allocate another petabyte of information because, you know, that's like 1,000 1-terabyte hard drives or 500 2-terabyte hard drives, which is a significant amount of hardware investment. Just to hold a list. And that's assuming you're doing this with hardware rather than, you know, well, anyway. Let me see what the chat says. Never use bubble sort. I agree. Binary search is good. Bubble sort is bad. Yes. If you want to know good sorting algorithms, quicksort is a good sorting algorithm. Merge sort is an okay sorting algorithm. Shell sort is a good sorting algorithm. In my C class, I taught shell sort a couple of weeks ago. Yep. The fastest way to sort a list is to have the list already sorted. Yes. Actually, there are some, believe it or not, sorting algorithms are one of the oldest areas of algorithms research, and there's still advances being made in sorting algorithms. The sorting algorithm that Python uses is actually a sorting algorithm called TimSort, which was developed in 2006, and the TimSort algorithm actually, it sort of searches for pre-sorted segments inside of the list, and then like maintains those and then sorts things around these in order to increase efficiency. In sort of rough terms, it's sort of one of the interesting things about sorting algorithms is there are adaptive and non-adaptive sorting algorithms. A non-adaptive sorting algorithm has the same runtime regardless of the sortedness or the degree of disorder of the list itself. So you can imagine degree of disorder as like a raw estimate of the number of spaces off that every element in the list is from the position that it's supposed to be in a sorted configuration. So bubble sort takes the same amount of time to sort regardless of the sortedness of the algorithm. So that means that its runtime is very, very stable, but it means that it does not advantage itself whatsoever based on the already whether or not the list is already sorted. Insertion sort is one step up from that, because what it does is it sort of grows a sorted list in the beginning of the list and takes every element and sort of passes it back until the list is sorted. So that takes advantage of sortedness. It doesn't perform those sorts of unnecessary examinations, but it can only reduce disorder by like 1 degree for each swap operation it performs. Shell sort is one step up from that, because it considers it performs swaps over like large spans of the array at once, so it can reduce it starts by reducing large amounts of disorder, and then goes to lower and lower gaps, and that reduces smaller and smaller amounts of disorder until you have a sorted array. Yes, it is harder to get an algorithm that is better than log base 2 of n. It is very hard. Will people find out a searching algorithm that is better than binary search? It's difficult. That's a difficult algorithm. To be honest, I don't know. But, I don't actually... My area of research isn't algorithms. But, I would not rule out the possibility, let's say. Let me put it this way. It would be difficult to do so in a computational system that's based on the binary system. Maybe quantum computing can do it. Yeah, cool. All right, so let's finish off these slides. So, functions as objects. In Python, functions are first-class objects. This means that we can use functions like objects of other types. And remember, since this is object-oriented programming, everything is an object. Even something like 3 is a scalar object. So, long story short, we can pass functions as arguments to other functions. All of you Haskell guys will be perfectly happy and familiar with this sort of formulation. This is why we say that Python can behave like a functional programming language. All you Haskell purists out there, I'm not sure if forcing all of the first years to take Haskell in their first semester is going to make them into Haskell purists or not, but generally speaking, people who come to an appreciation of Haskell later in life tend to look down their noses at other functional languages and languages that claim to have functional elements, because Haskell is the most pure and undiluted implementation of the functional paradigm. So yeah, Python claims to be a multi-paradigm language, but it's really just a object-oriented language with some bells and whistles thrown in. So, let's have the map function. All of you Haskell guys should be well familiar with map. What map does is it takes a list and it applies a function to each element of that list. So in this case, we're taking the function f as an argument. For I in range L at I is equal to f of L at I. So if we import math and we have the list 1, 2, 3, if we map cosine over L and then print L, what do we get? Good question. Let's Let's just tack this on here very quickly. Demonstrations are always good. Yep. Did I mess this up somehow? Indentation. Bloody indentation. Yeah, so you can see the cosine of 1, the cosine of 2, the cosine of 3. So because we have abstracted out the function that we're applying to every element in the list, this could be sine, this could be cos, it could be tan, it could be any function that you define as well. So it could be a function, like we could even apply, bin search. Although I'm not sure how you would do that precisely. The arguments aren't compatible. But, you could think of a way of doing something with it. So, we can also make anonymous functions. This is your equivalent in Haskell of a lambda. So, in fact, it even uses lambda. So, lambda is based on lambda calculus, which was an alternative computational scheme developed by Alonzo Church around the same time that Turing, well, actually slightly before, Turing was formalizing his idea of the universal machine, the sort of the Turing machine. Although I'm sure Turing didn't call it the Turing machine. That would have been a little bit arrogant. But anyway, so the general idea with a lambda is that you have some expression, and you can turn that expression into a function by extracting out the variables. It's based on substitution. So, for example, if we had lambda, if the expression that we wanted to lambdaize, as it were, was x plus 3, we would extract the variable x. If we then take that and apply the value of 6 to it, we get the value of 9. So it's called an anonymous function because there's no requirement to name it. Another way of talking about it is to call it an inline function. So, these things could get reasonably complicated. And if you want to have more than one element that you're performing the extraction over, then that's also perfectly possible. So yeah, lambdas are particularly, the sort of common usage for them in Python is using them in conjunction with the passing of a function as a parameter to another function. So if in our map example, rather than applying cos, we applied, for example, lambda x, shall we say the value is plus string x, something like that. Then we will get all of these strings in a list. So yeah, kind of useful for type conversions. Anyway, I'm going to check the chat. I don't think we have the time to start the next set of slides, but we will when we talk again. Good. Haskell has really made me appreciate Python. Yep. Haskell has its uses. I'm way out of frame. I would be cautious to say that Haskell is useless. Haskell isn't useless. It's just highly mathematical and abstract. There are cases in which Haskell is a practical language to use. It happens to be that, these tend to have more of an involvement with higher math, which means that Haskell, you may consider it an academic language, so perhaps the crux of your criticisms come criticism comes down to the applicability of Haskell within an industry setting, but don't imagine that Haskell is useless. If Haskell was useless, nobody would use it. Okay. So again, for those of you who aren't in comp sci and have not done Haskell, you just have to make the conceptual leap from a... You have to make the conceptual leap from functions as these sort of staid objects which are in some sense immutable inside of the structure of the program to things that can also be passed and stored and manipulated, because they are. They're just instructions, and those instructions can be stored and manipulated and passed around. You can even do this sort of thing in C, but that doesn't make C a functional language. Yeah, quantum computers are not going to be used for everyday... Well, like, the problem of, like, quantum isolation is a thing that requires, like superconductors and liquid helium cooling and all of these types of, like, really high advanced, physics processes that's very difficult to miniaturize. So it is unlikely that quantum computing is going to result in a sort of superseding and a replacement of electronic computing. Electronic computing, I think, is with us for the long haul, but it might be interesting that there will be interesting applications, I think. Yeah, quantum computing is a very interesting subject of study. I recommend doing some explorations of it. Ooh, and there's another interesting thing. It came across my news feed this week that apparently we now have room temperature superconductors. Although apparently apparently you have to like take the semiconductor and like squish it between two like hammer heads of pure diamond in order to apply enough pressure to put the material into a superconducting state. So it's still not practical, like for power transmission, which is kind of the like the hypothetical application of cheap superconductors is lossless power transmission. But yeah. Haskell will train you guys into more rigorous algorithmic thinking, which I think is kind of the point. Kind of confused on lambda. Do you not need to call lambda to process it through in the function? How do you call it? You don't have to... So we call it an anonymous function, but within the context of the function itself, it is being given a name. So if you take a look here, the name f is being applied to the lambda here, so that if you want to use this lambda inside of the function, you just call it by the name of the formal parameter, f. That's how you would access it. The trick is that this f doesn't have to just be this lambda, right? You could then, do another map down here and, like, do anything you want to it. Like, boys. And, you know, there you go, right? But yeah, anyway, hopefully that answers your question a little bit. Um, I wouldn't necessarily, Tyler, I wouldn't be too skeptical about the types of problems that can be solved. Um, while it's true that there is sort of different classes of problems and, like multiple core computers are particularly amenable to, these embarrassingly parallel operations, um, don't underestimate the ability of human creativity in shoehorning solutions to problems into paradigms that they were never meant to solve. That has happened many, many times. In fact, one might even think of computation, it's like the modern computer system, as being an expression of that. Um, Quantum computing is more likely to be more server-based for normal users in the future. I agree with that statement. Someone will run Doom on a quantum computer. Um, Possibly. Like, a version of Doom where, like, because of quantum superposition, you may or may not have killed the, whatever they call themselves, Caco demons? Yeah. Anyway. I think that's pretty much everything that I have to say today. Thank you very much, everybody, for your time and attention. Um, I guess I'll be seeing you next week. Ta-ra!